All right, hello everyone. What we're going to do today is review for the upcoming steel exam, which will be our first exam of the semester. And what I'm going to do is we're going to step through an exam. What I've done is I've shown you the types of problems you're going to see. And what I'm not going to do is do the whole exam because we've actually, as you'll see, we've done this before. So up till now, if you look at our lectures along with this, I think you'll be fine for the exam. So let's go ahead and get started. So like I say, we're going to review for the exam. Problem number 1, which is 10% of the exam grade, is a bunch of geometry. So it'll be something like this. We'll give you a shape and I'll say, what's the web thickness? So you'll have to tell me right there, what is the web thickness? So you'll have to look it up. And the web thickness, you'll recall, is T for thickness sub W. T sub W is the web thickness. Flange thickness, you'll look that up. That's T sub F for the flange thickness. And then I may ask for Ix, which means the moment of inertia about the X or horizontal axis. Or in this particular example, I ask for Iy. Okay, so all it is a matter of going to the table and looking it up. Good news is it's easy. Bad news is it's tough to give partial credit because you either got it or you don't got it. Okay? Let's continue. I'll give you something like this double angle you see at the top. And I'll say, what's the cross-sectional area? So you would look that up. Now, notice this is 2 angles. So don't go to the table with 1. This is 2 angles. And I'll say, how much does this weigh per foot? And I'm going to tell you the size of the angles. I took it out of this, but I'll tell you the size of the angles. It'll say like an angle 4 by 4 by 1/2. And that's how you would know where to look it up. So weight per foot, again, if you go to a table, there's a table in your book that is 4 double angles. And one of the columns says weight per foot. So you'll put that in. I ask you for a distance D. And that distance D, if you look in your blue book, that distance is given, but they don't call it D. They call it something else. So you're going to go find that distance. Don't worry about that they're calling it something different than D. And then you're going to report that as distance D. And then I'll ask for the radius of gyration with respect to the y-axis, r sub y. And you'll recall that there's an r sub x and an r sub y. And so what you're going to do, and there's even an r sub z when you get to angles. So you're doing, in this case, I'm asking you for ry, so you just look up ry. So again, so far everything you're doing is you're just looking stuff up from the blue book. And you can use this, what we're talking right here, it's a practice. You see what I'm asking you for, get your blue book, and you can look these up. Then I'll give you, if you look at the lower left-hand corner, I'll give you this angle, single angle. Now that stuff in that little red box over here in the corner, stuff in the red box will not be given on the test. I'm just putting that there to remind you. So I'll give you this angle, and again, I'll tell you the size of the angle. Maybe it's a 4 by 4 by 1/2. And so what is the thickness? The thickness is the last thing in the name of the angle. 4 means the one leg is 4 inches. The second 4 means the other leg would be 4 inches. And the very last thing that's listed in the example I just gave, which was 1/2, is the thickness. So you would just put that down. Then it says calculate the value of the moment of inertia with respect to the z-axis. And we had done this in class. You're going to go to the table. You can see an Ix in the table. You'll see an Iy in the table. You won't see an Iz. But you're going to recall what's in that red box there, that the radius of gyration is the square root of I over A. And since I'm asking for Iz, I'll look up Rz. And you can see at the bottom there, it says, there's the equation you would need. The moment of inertia is r squared times a. Since I asked for Iz, you're going to make it, which r do you plug in? Rz. So you're going to say that Iz, which is what I'm asking for, equals Rz squared times a. How do I get area, which is what a is? Look that up in the table. So this whole problem is all of that is 10%. Almost all of it is just looking some things up, with the exception of this, a little bit of calculations you have to do. All right. this is the last problem that's part of this 10%. I'll give you, for example, this channel, an MC 13 by 31.8, and I'll say, what's the depth? Now, you may be tempted to say the nominal depth is 13 inches, which is right, that's the nominal depth. But what you'll need to do is look it up in the blue book and see what the actual depth is. It could be 13 inches, or it could be 13.1 or something slightly different. I would like you to look up the actual depth. Then I'll say, what is the flange width? So you'll have to look up T sub F again, the flange width of the MC, in this case 13 by 31.8. Just looking things up in the book. The last one might be a little confusing. It says, what's the weight of 20 feet of this channel? Well, we know that the last number that's given in the name of a channel, in this case 31.8, that means it weighs 31.8 pounds per foot. That's how much this thing weighs, 31.8 pounds per foot. And I'm just saying, how much would 20 feet weigh? So all you would take is 31.8 pounds per foot times 20 feet, because I happen to ask you 20 feet, and your answer will come out in pounds, and that's what we're looking for this one. All right? So hopefully that's not too bad. It's looking some things up a little bit with computations. We just want to make sure everyone's clear with how to read from the table. All right? Next problem, and this is probably the most time-consuming problem. It's worth 25% of the exam. And so we're saying calculate I sub x. So the horizontal axis is the x-axis. So we're going to say calculate I sub x. And we're going to give you that beam that's in the middle there, we're going to give you the size. Whatever, W16 by 100, whatever the size, we'll give that to you. The channel at the top and the channel on the bottom, we'll give you that as well. I whited it out on this, but whatever, let's say it's MC 16 by 32, top and bottom. Now, the one thing I want to make sure, a lot of students miss this every year, look very, very closely. In addition to the beam, right on top of that beam, before the channel is in place, is a plate. So we have a beam and then a plate on top of it, the dimensions of which I will give you. And then we have a channel on top of that. If we look at the bottom of the beam, right when the beam ends, there's a plate, same size plate, and then a channel. A lot of students forget about that plate, and that changes the numbers. So what are we going to do to solve this? We're going to generate our table, right? If you remember that table, if you don't remember, put it in your blue book so you're ready. The table, if you remember the columns, it has part, area, y sub b, which is distance from the centroid of your piece to the bottom of the whole thing. Then you're going to have another column, which is area times y sub b, right? Then you're going to get into a column which is centroid of the whole thing minus centroid of your piece. The second to last column is area times this quantity squared, and the quantity I'm going to say is centroid of the whole thing minus centroid of your piece. You have all this in your notes. Just reminding you. And then lastly, the moment of inertia of the piece by itself. The total moment of inertia is going to be adding up the moments of inertia of the piece by themselves plus that parallel axis theorem piece, which is the AD squared piece, where again D equals centroid of the whole thing minus centroid of your piece. Now, if someone just came in and looked at this lecture for the first time, that seems like that's a lot to memorize, but we have done I don't know how many problems, and you have it in your notes. So it's just a matter of using the table. Couple notes though. Rather than break this down into a bunch of rectangles, do it by piece. The channel on the bottom maybe is one piece. I don't know if you want to call that number 1. The plate might be number 2. Then you have the beam, and the beam you might call number 3. Then you have the plate at the top, which would be piece number 4. And then lastly, you have the channel at the top, which might be piece number 5. So you would have 5 pieces. A couple of the things to watch out for. When you're filling out your table and you get to the very last column and it has IX, moment of inertia of the piece by itself, you're going to look in your blue book and you're going to say, what does the picture at the top of my blue book look like? If I'm looking at my beam, you say, is the picture of the beam in my blue book oriented the same way as it is on this problem? And this particular problem, the answer is yes. That's what your beam looks like an I-beam. And since this problem has it oriented the same way as your blue book, that means that you can use I sub x values because you're using the horizontal axis, which is the x. Now, if you look at that top and bottom channel, this is, again, just like one we did in class, the top and bottom channel, and if you look that up in your blue book, the channel is not oriented the same way it is on this picture that we're looking at. So it's like someone took that channel out of your blue book and turned it 90 degrees. Since we've turned it 90 degrees, when we fill out the last column of your table, we're not going to use IX. We've turned it 90 degrees. We're going to use IY. So in summary, IY is going to be used for the channels. IX is going to be used for the beam. The plate, if you try to look up properties of a plate, the plate is not in your blue book. The plate, the moment of inertia of a plate, is just 1/12 base times height cubed. So you'll have to compute that. All right. One last thing I want to mention. You're going to need distances from centroids to the bottom of your piece. So this channel, let's look at the bottom channel. If you look closely, there's a little tick mark at the bottom. That's the centroid of where the channel is. And the distance from that centroid to the back of that channel is in your blue book. So you want to remember that. And we were doing this in class. I think that there were some of us that thought that the channel centroid would be half the height, which it's not. If you look at the channel at the top and you look closely, there's that little tick mark again. That's where the centroid would be if the channel were oriented that way. So all we're asking you to do, compute the moment of inertia. It's a bunch of steps. We had done it before in class and was in previous lectures. So what I would suggest, the one we did in class was exactly like this, except there was no plate at the top and bottom. So what I would suggest is take the one we did in class and do it completely by yourself and then check the solution that I gave you. And if you made some mistakes, you can follow along to see where the mistakes were. Once you're an expert at that, then throw plates in and make sure you're ready for that, because this is the type of thing you're going to see for the exam. All right, so that's 25 points, your grade. Problem number 3 is a tension member. Now, anytime you hear tension member, all that means is you're going to turn to page 51 of your blue book, and you're going to use 2 equations. They're at the top, FT1 and FT2. That's it. When the members that you are pulling on with this tension load are plates, when they're plates, there is no U factor. We'll talk about a U factor in a minute. So here we have 2 plates. So you can right away say to yourself, 2 plates, no U factor. You may want to write that down so that you don't, make a mistake while you do it. So let's take a look. Calculate the allowable load for this joint. The bolts are 7/8 inch diameter, right? And this steel is ASTM A36. It's given. Okay. So since it's ASTM A36, if you look at your blue book, as soon as you open it, first page, we know that our Fy is going to be 36 kips per square inch. And our F sub U, our ultimate, is going to be 58 kips per square inch. That's always going to be the case for A36 steel. So what are we going to do? All we're going to do is plug into FT1 and FT2. So let's take a look. Here's the equation for FT1. Here's the equation for FT2. So if we want to plug in for FT1, it's 0.6 because it's a constant. Fy, which we just said in this problem is 36 kips per square inch, times Ag. That's as if this member breaks away from the holes. So what is Ag, or the gross area, going to be? It's going to be the thickness of the plate, which in this case is 1/2 inch, times the width of the plate, which I would give you, but I don't have shown right here. On the exam, of course, I give it to you. So if the width of this plate was 4 inches, our area would be 4 inches times 1/2. And that's how we would get our gross area. If you do the math, you get one answer. We're not done. You get one answer. Now you go to FT2, which is 0.5, which is a constant. F sub u, in this case, is 58 kips per square inch, times A sub n. Now, A sub n, what that is assuming that this member is going to fail right through the holes. And if it's going to fail through the holes, you're saying how much plate is left. I used to have all the plate, but now I punched 3 holes in it. So how much plate is left? Well, I take the area of the plate, first of all, and I subtract 3 holes. So I have 3 holes, so we're going to have 3 of them. The area of one hole is going to be the thickness of the plate times the diameter of the hole. Remember that, not the diameter of the bolt, the diameter of the hole. Okay. So in this case, the diameter of the bolt was given as, what was it, 7/8 of an inch, right? Yeah, 7/8 of an inch. So the area of one hole is going to be 7/8 of an inch plus 1/8 of an inch. We will always assume that a hole is 1/8 of an inch wider than a bolt. So the area of one hole that would wind up being 1 inch. So it's 1 inch wide by 1/2 inch thick. That gets me the area of one hole. I have 3 of them in this case. So how do I get my AN, my net effective area? It's just the area of the whole thing, which is AG. In other words, forgetting about the holes. And then I subtract out the holes. That's all it is. And we had done this in class. This is very similar to the homework problem that we did last class, which I sent you guys the solutions to. And that's it. Now you have 2 answers. Now how are you going to know which one is the answer? You're going to pick the lower of the 2. Think about it. What they said is, what load, let's get the exact wording. The wording is calculate the allowable load. So if someone gave you this joint and they said, how much load can I put on this before it breaks apart? You would say, well, I calculated FT1, I calculated FT2, and whichever one is smaller, that's your answer. So that's how you're going to do this part. Okay? This looks like when you look at this problem, it's a lot of words, seems confusing. It's not bad. We're going to give you a channel, not a plate, a channel. And we're going to say it's A441 steel. So right off the bat, you can say, well, A441, how do I know my yield or my ultimate for that? Again, look in the first page of your blue book, and you'll be able to look up A441, and knowing that we have a channel, and you'll be able to look up your F sub y and F sub u. During the exam, I'll probably help everyone to find that to make sure we're all on the same page. But it's on the first page of your blue book. So it says a channel made of A441 steel acts as a tension member in the bottom cord of a truss. Now, to be honest with you, you don't care. I don't care what it's used for. This is just more words that they're trying to confuse me with. All you care about is it's a tension member. Okay, as soon as you hear tension member, you think FT1 and FT2, just like the last problem. It says the member is punched for 3 rows of 7/8 diameter bolts. Okay. Why do you care about that? Well, we'll talk about that in a minute. So it's asked for 2 things. Part A says, calculate the allowable tensile load for a channel. So it's exactly like the last problem. But the last problem was plates. And if it was plates, we have no U factor. If you have any member other than plates, we have a U factor. So when we get to FT1, that first equation, we never ever have a U factor in FT1, ever. It doesn't matter if it's a plate, a channel, and anything. So when we calculate FT1, it's going to be done the same way as last time, right? It was 0.6 times Fy times Ag. How do I get Ag? I would just look up whatever channel I give you, look up the area, and that's it. And remember, the area is the entire area, not just the area of the flanges or the webs, it's the entire cross section. So FT1 is going to be 0.6 times Fy. Fy you're going to look up depending upon the type of steel, times Ag. Ag, you look that up in your blue book. That's how you get FT1. Never use a U factor for FT1. Now when you move to FT2, we will use a U factor unless we have plates. This one is not plates. So you're going to say, well, how do I know what my U factor is? Well, some versions of this exam, this is one version, I actually give you the U factor. Others, you'll have to look it up. If you have to look it up, you turn to page 51 of your blue book. It's in the middle and the bottom. And you're going to say, starting from the top down, there's 3 conditions. You start at the top, and you say, do I meet condition 1? If I do, I use that U factor. If I don't meet condition 1, I move down to condition 2, and I use that one. If I don't meet conditions 1 or 2, then I move to the last one, and I use that U factor. So FT2 is going to be the same as the previous problem, which was 0.5 times F sub U times AG. It's exactly the same thing. Area of the whole thing minus area of the holes. No difference. The only difference is then you're going to take that whole thing and multiply it by U, this U factor. And you'll recall the U factor is for shear lag. And any member that's not a plate has shear lag. It takes a longer time for the load to get into the member. Okay? So part A is going to calculate FT1 and FT2. Whichever one is the lowest, that's the one you're going to report to me. All right? Part B of this, let's see what it says. It says, if the member is 12 feet long, compare the actual and allowable slenderness ratios. And it tells you at the bottom, slenderness ratio is L over R. So that's not so hard. Actually, now that I look at it, at the very bottom, we're even giving you what the F sub Y and F sub U are. So you can see that as well. So what is the actual and what is the allowable slenderness ratio? The allowable slenderness ratio per our last lecture for any shape, L over R, recommended, should be less than or equal to 300. So right off the bat, you know what the allowable slenderness ratio is. It's 300. Hopefully you wrote that in your blue book. If you didn't, please do. What's my allowable slenderness ratio for a tension member? 300. So how do I check my actual slenderness ratio? Slenderness ratio is L over R. Our L value in this particular problem is 12 feet. Right? R is either R sub X or R sub Y. You're going to use whichever is smaller. You're going to look at R sub X, you're going to look at R sub Y. Whichever one is smaller, that's the one you plug into this equation. There is one trick though. Before you plug into L over R, don't just plug 12 feet in for L. When you plug L in, you want L to be in inches. Because L over R, you want those two things to be in the same units. And your R value, if you look up in your blue book, is already in inches. So when I tell you there's a length, in this case, of 12 feet, you're going to say, oh, okay, so my L is not 12 feet, it's 12 times 12, or 144 inches. So my actual is 144 divided by the minimum R value for this channel that I give you. Okay? So I'm going to give you a channel. You can look up R sub X. You can look up R sub Y. What is the actual slenderness ratio? It's the length divided by the minimum radius of gyration. And it says compare that. They're saying if the allowable slenderness ratio is 300, you can't go any bigger than 300, and you compute your slenderness ratio to be 400 or something higher than 300, that means that's not good. You're not meeting the code. Even if the strength is okay, if your slenderness ratio exceeds the allowable, it does not meet the code. So all we're asking you to do in part A is calculate FT1 and FT2. That's the first thing. And the second thing is compare the actual and allowable slenderness ratios. Okay? Last problem looks very confusing, but it's the easiest one in the whole test, to tell you the truth. This is the last problem. Using A36 steel, design an American standard channel. So we're going to tell you something like, in this case, go to page 18 of your blue book. So we're saying design a member, and all the members you guys pick are only going to be allowed to come from page 18, which is called American Standard Channels. We're telling you We want you to design it for a tension load of, and I'll give you the number here. Right now there's a blank. For a tension load of, whatever, 100 pounds. I tell you that the member is 18 feet long. The ends are welded. Why am I saying the ends are welded? Whenever we have a tension member, we have FT1 and FT2. FT1 assumes it fails not through the holes. FT2 assumes it fails through the holes. This problem is welded. In other words, this problem has no holes. And if this problem has no holes, then we'll never have to even look at FT2. FT2 is for holes, okay? So how would we do this one? We have to check two different criteria to do this design. First of all, we all remember that stress is P over A. So I'm asking you to design a shape. So you're going to rearrange that for A, and you're going to say that area equals load over stress. So what load? Let's say I told you the load was 100 pounds. So you'd say my P is 100 pounds. And then you'd say, well, what is my allowable stress? My allowable stress, because we have no holes in this thing, our allowable stress is going to come from FT1, which is from page 51 of your book. And FT1 is 0.6 times Fy. Right? Remember that equation? FT1 is 0.6 times Fy times A. So if we take FT1 and rearrange the equation for A, because remember, someone's saying, what size should we use? They're saying what area, that's how we're going to pick it. You're going to just take this equation and say the area I need is my load, which in this example is 100 pounds, divided by 0.6 times Fy. I know my Fy is 36 kips per square inch, and when I get done, I'm going to get an area. And it might come out to be, whatever, 12 inches squared. That's the area that I need. But that's only criteria 1. That's what I need for strength. Now we have to check slenderness. And our slenderness allowable is L over R has to be less than or equal to 300. So if L over R is less than or equal to 300, all I'm doing is I'm going to rearrange this equation for R, because I don't know what R is. And when I rearrange R, I see that the required radius of gyration is L over 300. So I'm going to plug in my length of my member. In this case, did I tell you the length? Yeah, I told you that the length of the member was 18 feet. So when I get to criteria 2, my L is going to be 18 feet times 12. I have to convert it to inches. 18 feet times 12 divided by 300. And that'll give me a number. So if I stop right now, that means I'm going to say criteria 1 tells me what area I need. Criteria 2 tells me what radius of gyration I need. Remember, when we use criteria 2, we're always talking about the minimum radius of gyration. In other words, it's the smaller of either Rx or Ry. So this problem's actually done now. All you're going to do is you're going to go to, let's see, what did I say in here? I said go to page 18 of your blue book. So go to page 18 of your blue book. You're going to pick a shape that has an area of at least the area that you computed by criteria 1, and the same shape that has at least the minimum radius of gyration that you computed. So you're going to look at R sub x and R sub y. I would do it with a table myself. I would say, I'm going to pick this shape. Here's the area, here's the minimum radius of gyration. And then I look at my required. Does this shape meet that requirement? If it does, yes. And you go to another, well, maybe, what if I want a little lighter, something a little smaller? And I write that down. Does that work? Yes, maybe that one works too. And you keep going, you're going to get to a point where shapes don't work anymore. So you're going to give me a shape that meets these two criteria, that's for sure. But try to give me one that's light. Don't just turn to this page and pick the biggest one on the page and say, here, this will work. So this is all we'll have to do is criteria 1, criteria 2. After you do those two, then you report to me the lightest one that does satisfy these criteria, and you're done. And that's exactly, by the way, how we do tension member design. It's a piece of cake. All right. So that's all we have. Excuse me. That's all we have for the exam. First problem you'll recall, like we said, is the geometry. Looking things up in the book. Couple quick calculations for I sub z for a single angle. Quick calculation for how long a 20-foot length of a channel is. Problem 2 is a moment of inertia with that table, which we had done. Problem 3 is FT1 and FT2. It's a plate, so there's no U factor. Problem 4 is a tension member. Again, it's FT1 and FT2, but we do include a U factor when we consider FT2, since it's not a plate. FT1, no U factor. And then the second part of this is we have to compute the actual and allowable slenderness. And then the last problem is that design. And how do you do the design? You just calculate the area you need, that's criteria 1, and the radius of gyration you need, that's criteria 2. Remember, in order for you to get credit for this, you have to give me something that satisfies both criteria. If you say, well, I got an area that's fine, I'll say, yeah, but your radius of gyration or slenderness is not acceptable. Or vice versa, you have to have something that's acceptable for both. All right? So what I would suggest, please take a look at this. You have the solutions from homeworks where we did examples like this. Please practice. If you have questions, let me know. Our schedule is on Wednesday, which would be what? Wednesday the 24th is when we're going to have the test. And you should be fine. If you